Hello friends, my name is Steven, and today we will be doing a crash course in intermediate microeconomics. We're going to try to do it all in one video. I wouldn't recommend learning the content like this, but I will try to cover all of the relevant topics and subtopics. So let's get right into it. Basically, we're going to start with trying to define a rational decision maker. We want to be able to analyze people and their decisions and predict their decisions. We want to be able to do that mathematically. And so in order to do that and to be able to use functions and all this other mathy stuff, we got to meet some assumptions, okay? And here are the assumptions. Here are some basic assumptions we need to meet. If I'm defining a rationalist decision maker, number one, I want their preferences to be complete. This is going to be one requirement. Basically, if I give you two options, A and B, you need to be able to say, I prefer A to B, I prefer B to A, or I am indifferent between A and B. So either A is preferred to B is preferred to A, or I am indifferent. We'll denote that like that. If you say, I don't know what to choose, then you don't fit our rational decision-making model. We can't put you in a function because I can't predict your behavior if you don't know what your preferences are, okay? So they need to be complete. They also need to be transitive, meaning that if A is preferred to B and B is preferred to A, then it logically follows that and B is preferred to C, it logically follows that A is preferred to C, okay? You prefer one thing over another, you prefer that thing over another thing, then logically, then A must be better than C, right? We don't want any of this circular decision-making going on. We also want them to be continuous. This is more of a math-related thing, but we want your preferences to be smooth. We want them to fit well into the function mathy world. We don't want any sudden jumps in preferences. We want all of those to be gradual. Okay, so complete, transitive, continuous. Those are our axioms of rational choice, rational decision making. Okay, and if we meet all of those, then we can put your behavior into some kind of function that we'll call a utility function. Okay, like this. Utility equals xy. Utility meaning happiness or benefits or whatever you want to call it. But we're saying you get utility in life from only these two things. That's what this function says. Anyway, this particular one is a very simple one. So this person gets utility from the combination of two goods, x and y. In fact, in this example, they get it multiplicatively. So if they have 0 of either one, their utility is going to be 0. So they need some combination to be happy or be benefited at all. Okay, so a graph of this utility function, we're going to attempt to graph this, and it is a 3-dimensional graph that we're going to graph in 2 dimensions, and we're going to do that with contour lines. So basically, we set utility to be some constant number. Let's say utility is 5, so here's our graph. Where utility equals 5, that's a relationship between x and y. We'll draw another contour line. This is where utility is 10. Let's draw another one when utility is 15. So this is what our graphs of u equals x, y looks like, graphing a 3-dimensional function in 2 dimensions, okay? We want to be on the highest of these contour lines possible, and we're going to call these indifference curves, okay? We call them that because for any two bundles, let's say a bundle here of x and y and a bundle here of x and y, we are indifferent between those two combinations of x and y, okay? We don't care what the combination is because our utility is 5 in either situation, all right? We just want to maximize our utility. We want to be on the highest indifference curve possible. That is our whole goal in life. Okay, so that's what we're going to try and achieve. Okay, so let's say we have a utility function that looks a little bit different, like root xy. All right, utility, as you can see, is kind of an abstract concept. So because utility is an abstract concept, it doesn't really, like, what does it mean to have 5 utility? No one knows. Okay, so all we care about is that 10 utility is better than 5 utility. We don't define how much better it is because we don't have a way to define that. So what I'm saying is utility is ordinal. Ordinal meaning 10 is not some amount better than 5, it just is better than 5. The ranking matters, but the numbers don't matter. Because utility matches that definition, we can actually transform a function like this into an easier one to work with. I'm just squaring this function. And by squaring the function, I'm creating u equals xy. Not u squared. I don't have to square u because, again, I don't care about the units of u. So I'm squaring this right-hand side to make it easier to work with. U equals xy. We call that a monotonic transformation. I'm taking some function g of u, in this case, It was u squared. And it has to be a function that is monotonically increasing. U squared, monotonically increasing. If we took g of u equals 1 over u, not an increasing function, okay? This is the graph of 1 over u, definitely not increasing, okay? But I could take, say, g of u equals log u. The graph of log u looks like that. That is an increasing function, so that would be an acceptable monotonic transformation that I could apply to a utility function, okay? So that's monotonic transformations, that's indifference curves, and let's look at some, oh yes, let's talk about the relationship between x and y, because we actually care about the utility we get from these goods. We care about the marginal utility we get from these goods. So like, what is the change in u with respect to some x? 1 unit of x increase, how does that affect our utility? That is the marginal utility of x, or we can also denote that as ux, right? And we'll denote the marginal utility of y as uy, okay? We're interested in how much utility we get when we increase our x or y by 1 unit, but we're also interested in the relationship between those. So we're going to call that the marginal rate of substitution, which relates x and y to, or relates the marginal utility of x and y to each other. That's important. And what's also important is the prices of x and y. We're going to be interested in how this relates to the ratio of prices between them, because if the ratio of prices and the marginal utility are off, then I'm going to want to buy one good over the other, because the marginal utility I get relative to the price is going to be more beneficial for me than the other good. We'll see that a little bit later in a second. But so this is the marginal rate of substitution between x and y. And we also care about the price ratio. We covered monotonic transformations. So let's look at some more examples of utility functions. So let's say u equals x plus y. Okay, so these are the indifference curves for a function like that. These are perfect substitutes. You can perfectly substitute x for y at any point right there. Okay, let's say that one good was more expensive than the other, right? What you would end up doing is you would just go all for one good. You want the good that has more bang for your buck. You're not caring about a combination. Just whichever one is better. You're going to choose all of that. So you're actually gonna your maximum utility is going to be at one of these corners right here. Let me show that with something called a budget constraint, right? Because x and y have prices, and you're maximizing utility. You're not just going up and up and up because you have some amount of money to spend. You don't have infinite money, right? And we're going to say, since we defined x and y, we said like with this function, all of your utility in life, all you care about is just x and y. And that's it. You don't care about anything else. So it would follow logically that all of your income you're going to spend on either x or y. We're going to make that assumption. We're going to say that your income equals x times the price of x plus y times the price of y. And that is going to be what we call your budget constraint. We can actually graph your budget constraint here. Let's say you can buy, this much x if you go all x, or this much y if you go all y. We'll just graph a little budget constraint right there. And okay, that's what that looks like. And with your budget constraint, you're going to want to be on the highest indifference curve possible, okay? And what that means is that your budget constraint is going to be tangent to your indifference curve. And you're going to consume the bundle of x and y that gets you there. So this person with these indifference curves and this budget constraint will consume this much x and this much y. There we go. We have now predicted someone's decisions and the optimal amount of x and y to produce, or for them to consume in order to get their maximum utility. Way to go, we've done it. A budget constraint over here would look kind of more like this, right? And the highest indifference curve would be at some corner. You would hit some corner of that indifference curve. And so you would go for all of one. That's perfect substitutes. Perfect complements would look like this. Okay, it's an interesting graph for perfect complements. That's the graph of u equals the minimum of x and y. You keep increasing one, and it doesn't matter because you want a certain amount of both of them. All right, you got to get them both together. Look at one more. This is going to be u equals x squared plus y squared. And this is the equation of a circle, obviously. And the first quadrant looks like this, so you get these kinds of indifference curves. All right. Notice that these are different than the other ones. And these other examples, these are concave, right? We'll call them, so they're bowed inward towards the origin, or this one is not strictly concave, but we still call it concave, Because as you can see geometrically, if you took 2 bundles of any of these goods, then you would prefer an average to the extreme, right? You would want the average right here because that puts you on a higher indifference curve, right? But notice that right here, if you took 2 bundles, you would not prefer the average right there, right? Averages are not preferred to extremes. In fact, in this case, I mean, you can see that with this function right here, you have diminishing marginal utility. The more x you get more and more and more and more x, you care less and less. You're like, well, I already have a lot of x. Like, it doesn't matter that much that I have 1 more x. Whereas here, it's the opposite. As you get more and more x, you actually want more and more and more. This is referred to as the addiction model. So what you'll end up is with another corner solution, kind of like the perfect substitutes. You're either going to go here, like let's say this is your budget constraint. You're going to go here or here. That's going to be your optimal place to go, assuming that this is your utility function. Okay, that's geometrically how we determine convexity. These are not convex, these are concave indifference curves. This is a concave utility function. But if we wanted to determine that mathematically, what we would do is we would take the derivative of the MRS with respect to x. So let's see over here. So we have the MRS over there. So the marginal utility of x, right, du dx, that would be y. Marginal utility of y would be x, so you have y over x. So this would be derivative of y over x with respect to x, which is going to be negative y over x squared, which is less than 0. And if it's less than 0, it's concave. In fact, if it equals 0, I think it equals 0 in this case. Let's just check that really quick. So you would have, well, marginal utility would be 1 over 1 equals 1. So the derivative with respect to x, that would be 0. Yeah, so that's not strictly concave, but we do call it, or sorry, not strictly convex, but we do call it convex. All right, this is convexity. All right, so this is a convex function. This is a concave function. So we'll take the marginal utility. So let's see, the MRS is going to be marginal utility, let's see, 2x over 2y. It's going to give you x over y. If you take the derivative of that with respect to x, that is going to give you 1 over y, which is more than 0. So it's concave, okay? Not convex. All right, so that is convexity, that is indifference curves, monotonic transformations, all that stuff. But at this point, let's go ahead and look at how we actually maximize utility, okay? So we have a goal, maximize utility. We have a constraint, that's our budget. So let's write this. This is our objective function. Our objective is to maximize our utility by choosing x and y, okay? Subject to some constraint, which is that our income equals x times the price of x plus y times the price of y. Okay, and the way that we solve this problem, choosing these 2 variables, is with the Lagrangian method. So to write a Lagrangian, you're going to take your objective function, and you're going to plus lambda times, and technically this is 0, but you're going to take your income minus xpx minus ypy. So that is 0 because the income minus income. But adding this variable lambda is going to allow us to solve this constrained optimization problem. So the way we do that is we take the derivative of your Lagrangian with respect to x. You're going to get y minus lambda px. The derivative with respect to y is going to be x minus lambda py. And then the derivative with respect to lambda is the last one you're going to take, and that's just going to be your constraint, I minus xpx minus y py. You're going to set these all equal to 0. These are your first order conditions. Okay? And then you're going to solve for lambda, and you are going to plug them in. And what you get is y over x equals px over py. And notice here that what you ended up with is your MRS equals your price ratio. Look at that. That's the marginal rate of substitution for u equals xy. And this is the price ratio, px to py. This is actually always going to be true at the optimal point. Okay? If this was not true, if your marginal rate of substitution was not equal to the price ratio, then you would get relatively more marginal utility from buying one good over the other relative to the prices. And so you would prefer buying that good. So you're going to continue to balance out the amount of the goods that you buy until you hit an optimal point. And that optimal point is where the MRS equals the price ratio. Okay? We call that Jevons rule. So we can continue this problem. We can solve for y. That's going to be x, px over py. And we'll plug this into this bottom function right here and get I equals x px. That's supposed to be minus I minus. Oh, yeah. I moved it to the other side. Okay, we're good. I equals x px plus x, or yeah, x px over py minus py. There we go. Sorry about that. Okay, so we get 2xpx is I. Solving for x, we get I over 2px. And actually in this case, because of our utility function, y is symmetric. So it's I over 2py. And there we go. There we have it. Those are our optimal bundles of x and y. You tell me an income, and you tell me the prices of x and y. I will tell you the optimal amount of x and y that this consumer will consume, trying to maximize their utility subject to their budget constraint. Okay, so notice right here that these functions, these are homogeneous of degree 0. What that means is that if we multiply everything measured in dollars here, income and prices, if we multiply that by some constant, then what we'll end up with, the 0 means that it will not affect our function at all. But let's just try that. So we got ki over 2 kpx. We're multiplying the I and the px by some constant k, and what those k's are actually going to cancel out. So what this ends up being is k to the 0 times our initial function, right? X star, k to the 0 x star. And this 0 means it's homogeneous of degree 0, okay? Which makes sense. In fact, everything about these functions makes sense. If I increase my income, then I buy more x. If the price of x rises, then I buy less x, okay? So that just makes sense. And if I increase income and prices, let's say inflation happens and income and prices increase by the same amount, then the amount of x and y I buy actually will not change at all. So they're homogeneous of degree 0. All right. So let's talk about this concept of how this would look if let's put this on a graph. So we have an indifference curve, we have a budget constraint, let's say they're tangent, and that's where we're consuming x and y. And let's say there's a change in one of these, change in the prices. So let's say the price of x goes down. If the price of x goes down, then I can buy more x. So I can buy just as much y, so we'll leave that here, but my new budget constraint will look something more like that. Okay, so this is my new budget constraint, that line that I just drew. And so this is what's going to happen. So I'm gonna end up on a higher indifference curve, right? I can go higher now. So I'm going to do something like that. Okay, it's kind of funky looking, but whatevs. Okay, so let's pretend, oh, these aren't very good. Let's pretend that's tangent right there, and that's tangent like right there. Okay, so I'm consuming more x and more y at this new indifference curve, but that's because of two things. That's because of the substitution effect and the income effect. Okay, and I can actually decompose those. I can separate them into two actions. So the first thing that happens is let me take the slope of my budget constraint and just like move it down here. This is the first thing that happens. Wherever that slope is tangent on this line, that's the first thing that I do. The first thing that I do is I substitute away from y. The price of x goes down, remember. So I'm going to substitute away from y, and I'm going to buy more x. More x, less y, that's the substitution effect. But then, because the price of x is lower, my income has also gone up. And because my income has gone up, I'm going to go to a higher indifference curve. Okay? And that is going to be the income effect. Okay? So I've now decomposed this phenomenon into the substitution effect, where I move along my current indifference curve, and the income effect, where I move to a higher indifference curve. And that's kind of a key concept, is decomposing those two effects. If I were to express this graphically, there's another type of demand. This is what we call Marshallian demand, named after Marshall, obviously. So that is the substitution effect and the income effect are encapsulated there. But there's also Hicksian demand, named after Hicks. And this is Hicksian decomposition right here. And what Hicks did with his demand model is he pushed out the income effect, just focused on the substitution effect. Okay, so it doesn't take into account the income effect. It's also called compensated demand, like XC, or x Hicksian, either one, for that reason. It compensates, it says, how much do I have to spend to get a certain level of utility is how Hicksian demand works. And I'll explain that more in a second, but basically this is how the relationship might look between Marshallian and Hicksian demand. And let's say we're consuming at some bundle here, x star, and this is x and this is the price of x, okay? So let's say that the price of x goes down. If the price of x goes down, then a couple things are gonna happen. One, I'm gonna move to this new point. This is Hicksian demand, so that's the substitution effect. Marshallian demand is gonna be out here. And that movement right there is the income effect. So Marshallian takes into account the substitution and income effect. Hicksian, just the substitution effect. Okay, so that is how the substitution effect and the income effect play out together. What else do I want to say about that? Yeah, let's talk about, so the Slustky equation also is a way to decompose this. So the Slustky equation says that the change in Marshallian demand, so let's observe this graph right here and let's express it mathematically. The change in Marshallian demand with respect to the price of x equals the change in the Hicksian demand with respect to the price of x minus the change in Marshallian demand with respect to income times the amount that I was consuming before. Okay, so how does my income change? Or how does Marshallian demand change with a unit increase in income? And how much did my real income change? This is the substitution effect, and this is the income effect. Okay, so that is the Slustky equation, the own price Slustky equation. There are multiple Slustky equations. This is the own price Slustky equation that substitutes into the substitution effect and the income effect. And so that's Slustky decomposition right there. And one more thing about that before we move on and do an example is we can decompose this into the concept of gross and net substitutes and complements. And what do I mean by that? Well, gross, I'm referring to Marshallian demand. I'm calling it gross because it includes the substitution effect and the income effect. Okay, so that's Marshallian demand. Whereas net, I'm calling that because it refers just to the substitution effect. That's Hicksian demand. And gross and net substitutes and complements, I'm going to say a substitute is something where the change in x with respect to the price of y, so this is cross price, is more than 0. So the price of y goes up and I buy more x because I'm substituting away from y. That's a substitute. If it was less, then that would be a complement. The price of y goes up, I buy less x because they're complements. I need them together. Okay, so because of this, I can define gross substitutes as the change in Marshallian demand with respect to y is more than 0. Net substitutes, the change in Hicksian demand with respect to price of y is more than 0. Gross complements, change in Marshallian demand with respect to the price of y is less than 0. And net complements, the change in Hicksian demand with respect to the price of y is less than 0. Okay, so that's everything about the substitution effect, the income effect, and how we decompose them with Hicksian decomposition, with the Slustky equation. Let's actually look specifically at how we solve this Hicksian problem, because how Hicksian demand works is, like I was saying, so instead of saying I'm going to maximize utility subject to some budget constraints, I'm going to say, okay, how much do I have to spend to get some level of utility? So here you have some fixed income and you're maximizing your utility with that income. In Hicksian demand, you're minimizing your expenditure to get some set utility. So it's kind of flipped. This is the way it works. So you're minimizing, you're choosing XY to minimize your expenditure, XPX plus YPY, subject to some constraint, U bar equals XY. Okay, and so this is how the Hicksian decomposition works, or the Hicksian problem, I guess, if we're going to solve for Hicksian demand. You're going to take a Lagrangian again, and you're going to go through much the same process, but now this is your objective function, and this is your constraint, or this is your objective function. So now your objective function, xpx plus ypy, plus lambda times your constraint, and you're going to have u bar minus xy. That's how that's going to go. You're going to take your derivative with respect to x and get px minus lambda y. All right, take it with respect to y, get py minus lambda x. And then take it with respect to lambda and just get your constraint u bar minus xy. Solve for lambda, plug those in, you're going to get px over py equals y over x. Again, your price ratio equals your MRS. In this case, we're going to get the same thing, y equals x, px over py. Plug that in here. Sorry, all these are equaling 0. These are first order conditions. U bar is going to equal then x px over py. Therefore, x squared equals u bar py over px. So your Hicksian demand for x is going to be root u bar py over px. And in this case, your Hicksian demand for y is going to be symmetric. It's going to be root u bar px over py. You can see that this makes sense. As the price of y rises, you buy more x. You're substituting away. As the price of x rises, you buy less x. So these are in terms of u bar and prices instead of being in terms of income and prices. All right, so that's the difference between Hicksian and Marshallian demand. Notice that these are HOD zero still. So if I multiply, and you're not multiplying utility, just the stuff measured in dollars. So prices of y, prices of x, I'm going to multiply those by some constant k, and I'll get k over k, and I have not changed the amount of x and y that I'm going to consume. Okay, so that is Hicksian demand and all that stuff. And I think at this point we're gonna erase all of this, and we're gonna look at kind of a bigger picture representation of a lot of these concepts in consumer theory and how they fit together. So essentially, let's recap. So if I want to maximize my utility, which is in terms of x and y, subject to some constraint, income, which is in terms of x, y, and their prices, then performing a Lagrangian, that's going to give me x Marshallian, right? And that's going to be in terms of income and prices. Okay, over here, if I want to minimize my expenditure, which is in terms of x, y, and prices, subject to some constraint, u bar, in terms of x and y, then performing a Lagrangian, I'm going to get Hicksian demand, which is in terms of u bar in prices. Okay, that's how those work. Now we're not done. Okay, so we can actually take this a little bit further and plug in our demands back into our initial function. That was our objective function. Okay, so let's go ahead and do that. So what was my x Marshallian? It was I over 2 px. What was my x Hicksian? It was root u bar py over px. Okay, this is my Marshallian and Hicksian. So I'm going to plug these back into my initial function. So u equals xy becomes u equals I over 2 px, I over 2 py, which is I squared over 4 px py. I'm going to call that indirect utility. I'm going to represent that with a v. So it's indirect utility because it's now in terms of income and prices. So I know that I can plug these into my objective function. Let's just put it like that. And what I'm going to get is I'm going to get indirect utility, which is in terms of income and prices. I'll just put this in terms of like x star and y star, the optimal x and y, but you can see that those are in terms of income and prices. Okay, so I plug it back into my objective function, I get indirect utility. And in a similar way with Hicksian demand, I plug it back into my initial objective function, which was I. Okay, plug objective function, which is I here, and what I get is an expenditure function. Okay, so basically instead of calling it I, I'm calling it E. So there I change the U to a V, here I change the I to an E. I get an expenditure function that's in terms of my x star, my y star, which is in terms of utility and also prices. I mean, yeah, prices are in there, but prices are also in my X star and Y star. So yeah, you get your indirect utility, you get your expenditure, you get those both ways. And you can actually go back to these. If you are given an indirect utility function, then you can actually use formula negative derivative of your indirect utility with respect to X over derivative with respect to income. That will give you your initial X Marshalian. This is Roy's identity, after our boy Roy. And it's even easier over here. You can just take the derivative of your expenditure with respect to X, and that gives you your X Hicksian. This is Shepard's lemma, okay, after Shepard. All right, so you can also switch between indirect utility and expenditure very easily. I have this indirect utility function. All I'm going to do is I'm going to change that I to an E and that V to a U bar. So I have E squared over 4px py equals U bar. Okay, and I'm going to solve for E. E squared equals 4U bar px py. And so E is going to equal 2 root U bar px py. Okay, expenditure and indirect utility. You'll notice that indirect utility is still HOD 0. Okay, k squared over k squared. All right, so that does not change the initial function at all if we multiply income and prices by some constant. But look here at the expenditure function. If I were to multiply these by some constant, 2 root U bar kpx kpy, I would get a k squared in there. I would pop it out as a k. And so it would equal k to the 1 times my initial function. And that means that this is HOD 1. Expenditure functions are HOD 1, which makes sense, right? If I multiply all prices by some constant, then my expenditures will be multiplied by that constant. Okay, so all those other ones are HOD 0, but expenditure functions are HOD 1. And the only other thing that I feel like covering right now is elasticity. I feel like that's a pretty good topic for economics. So the elasticity of x and some other thing t is going to equal the derivative of x with respect to t times t over x. Here's a little useful formula for elasticity. You could apply that to own price elasticity, x and px, cross price elasticity, x and py, or income elasticity, x and income. For example, for cross price elasticity, you just plug in py for t, and you get your little formula there. Elasticity is also interesting because let's say I take my Marshallian demand of x equals I over 2px, and I take the log of that, then the log of I over 2px is going to equal the log of I minus the log of 2 minus the log of px. And the coefficients on these are going to be my elasticities. So here's the coefficient 1. That is the income elasticity of x. -1 is the own price elasticity of x. And the cross price is actually 0 because there's no py in this function here. But if there was a py in this function, it would be plus a py over here. And this a would represent the cross price elasticity of x. So that is consumer theory. And then we'll move on to producer theory next. All right, guys, so let's get into producer theory. All right, now we're not looking at the behavior of consumers here, but we're looking at the behavior of firms and how they make decisions. And we're going to use that later along with consumer theory to go into partial equilibrium theory. But today, let's look at how firms make decisions. But there are some concepts from consumer theory that will carry over here really well. So let's talk about production functions. So basically, firms are going to make decisions in terms of these functions that we're going to say their output or their quantity is dependent on some inputs that they put in, right? So right now, we're going to assume that those inputs are labor and capital. There's a certain amount of labor hours that they hire, and there's a certain amount of capital hours that they hire as well. We'll talk about that a little bit as well. But let's just assume we have some production function that looks like this. We have L to the 1/3, K to the 1/3. Okay, this is some combination of labor and capital that this firm produces. We put that in and we get some amount of output. And so we can graph this, and we can take a look at what this graph looks like, and it's another three-dimensional graph that we're going to graph with contour lines. So this graph is going to look like this, and let's say that's a bad line, but whatever. These are also called level curves, if you're wondering. Let's say that's when quantity is 10, that's when quantity is 15. Okay, and this is a Cobb-Douglas production function. Okay, so we have some combination of labor and capital that gives this graph. That's labor and that's capital right there. And we can look at the relationship between these two goods and how they affect the output that we produce as a firm. We'll look at, how well can we substitute these things? So we're going to call these, because this is a combination of labor and capital that we can use to produce this output. And so as we substitute them, we'll still get this output if we're on this curve. So we'll call them isoquants, meaning same quantity. Okay, each of these curves. So they're a lot like indifference curves from consumer theory, but now they're called isoquants. Okay, combinations of labor and capital. We're going to be interested in the marginal amount of labor. Let's say the change in quantity with respect to labor. We're going to call that FL. I could call it QL, but I'm going to call it FL because that's pretty standard in how it's taught. But this is the marginal product of labor, or this is also called the MPL, right? And then we have the marginal product of capital. We're interested in both of those things, right? This is familiar to consumer theory. The relationship between both of these things we're also interested in. We'll call that the marginal rate of technical substitution. Kind of like the marginal rate of substitution, but now it's technical, all right? So we're interested in the relationship between those things. Something else we're interested in is the returns to scale for this production function. So as I scale up my firm, how does scaling up affect the returns I get in terms of how much output I can get? So we notice that this production function, I'll write it again right here. All right, if I were to scale up my labor and capital, how much I put in by some constant, I'll call it A in this case because we're already using K. But if I were scaled up by some constant A, and what I would end up with is, in this production function, is a to the 2/3 times my initial production function. Do you see that? A to the 1/3, A to the 1/3 becomes a to the 2/3. So because this is less than 1, this production function has decreasing returns to scale. All right, as I scale up, my returns are relatively decreasing. If this was, L to the 1/2, K to the 1/2, then I would have constant returns to scale. If it were L to the 2/3, K to the 2/3, then my A would end up more than 1, and I would have increasing returns to scale. As I scaled up and up and up, those returns would be increasing. Okay, so we're interested in the returns to scale for these different functions because that tells us about the structure of our business. And another thing we might be interested in when we're assessing our production functions is how easy is it for me to substitute one input for another? How substitutable are labor and capital? Can I just get rid of one of my machines and hire more people and it's like the same thing? Or are they not really substitutable? So we can measure that by just saying, hey, what is the percent change in our capital labor ratio as I make some percent change in my marginal rate of technical substitution? So in other words, as I move along this curve, then how does the ratio between labor and capital change? If it's high, if they're very very substitutable, right? There's a huge response in the capital labor ratio as I change my marginal rate of technical substitution. They're very highly substitutable, or they could be not very highly substitutable, right? I move along the curve and there is very little change, okay, in the capital labor ratio, so they're not very substitutable. Let's call that. This is actually the same kind of thing as the derivative of the log of the capital labor ratio with respect to the log of the MRTS. And that can be helpful in deriving it. But we'll just call that, it's a similar concept to elasticity, right? We're kind of asking how elastic is substituting between labor and capital, our inputs. So we'll call that the elasticity of substitution, and we'll denote it with a sigma. That's a sigma up there. Okay, so these are all things that we can consider and things that we'll be interested in as we're assessing our production functions. Okay, so this is our Cobb-Douglas production function. So we already assessed that the returns to scale for this function depends on what the exponents are between L and K. And actually, the MRTS also depends on what the exponents are as well. But the interesting thing about the Cobb-Douglas production function is that the elasticity of substitution, that's a bad sigma, but whatever, is always going to be 1. So that's for Cobb-Douglas production functions. Elasticity of substitution is 1, and we can use that to, they're relatively substitutable, and we can use this as like a benchmark as we look at other examples of production functions. So let's look at a couple of other examples. This is a linear production function. Q equals 2L plus 3K. Okay, these indifference curves, or not indifference curves, sorry, isoquants would look something like, I'm bad at graphing, but they would look something like that. Okay, so this is a linear production function. Okay, the returns to scale on this are constant, and the MRTS is also constant. If we took, the marginal product of labor, that's 2, marginal product of capital, that's 3. So the MRTS is actually 2/3, and it's always going to be 2/3 no matter what. So it's got a constant MRTS, and the elasticity of substitution on this, because it has a constant MRTS, there's no, there's no percent change in the MRTS, right? That's going to be 0. So actually, these are going to be infinitely substitutable, infinite elasticity of substitution, because they're perfect substitutes, right? I can change some amount of machine hours for some amount of labor hours, and it really doesn't matter. And I say machine hours because it makes our units easier to deal with. We have labor hours, and then to make it so that we're assessing these in a way that makes sense, we have machine hours. So basically we have some wage rate W. That's how much it costs to hire labor. All right, just like in consumer theory, there are prices for these things, right? They're not free. And so this is the price of labor. It's the wage rate per hour, and then we have labor hours. And so capital is a similar thing. We have these machines. We have a lot of different other types of capital, like I guess you should have like real estate and but whatever. We'll just keep it to machines right now, and we'll say that there's some value of those, and it's and we'll call it the rental rate for those machines. So we'll basically value them at some per hour rate of renting this machine, and that's the value of our machines, and we're multiplying it by machine hours. So that's how we keep our units in check there. So anyway, essentially we're saying that one of these labor hours, one of these machine hours is perfectly substitutable in this production function. Okay, now let's look at a different case. All right, this will look familiar from consumer theory. This is when Q is the minimum of some portion of labor and capital, right? They don't have to be exactly equal, but basically we have to have fixed proportions of labor and capital, and that's how our production function looks. This also has constant returns to scale, but the MRTS is not really defined actually. So I mean, if you're at this point and you move to this point, then I mean, you're changing your labor, but there's no change in your capital. But if you're at this point and you move to this point, then there's an infinite change. So the MRTS is not really defined, and actually the elasticity of substitution is going to be 0. These are not substitutable whatsoever. Okay, you cannot make any comparison changing labor for capital. You have to have them in fixed proportions. Okay, let's do one more. This is kind of an interesting one. So let's do Q equals 1/3 K to the 1/2 plus 2/3 L to the 1/2, all of that squared. Okay. Yeah, this is a little bit different of a production function. It follows this general formula of let's see if I can remember. It's AK to the rho plus 1 minus A L to the rho, and it's all of that to the 1 over rho. Yeah, this is a weird one. Where am I going with this? Well, in this case, the graph is going to look kind of Cobb-Douglas-like, at least in the case that I drew right here, where I put these numbers up here. But this is actually a special kind of production function that we are interested in, because the elasticity of substitution is going to equal, all the time, it's going to equal 1 over 1 minus rho. Okay, it's going to be constant. It's not going to depend on K and L. but it's 1 over 1 minus rho all the time. So we call this a constant elasticity of substitution function. And you'll notice actually that all of these functions are special cases of the constant elasticity of substitution function. In fact, when rho approaches 1, for example, then we have something akin to fixed proportions or perfect substitutes over there. As rho approaches 0, wait, no, I said rho approaches 1. Yeah, that's right. As rho approaches 0, we have Cobb-Douglas, and as rho approaches negative infinity, we have fixed proportions. Did I call this fixed proportions? Sorry, this is not fixed proportions. It's linear over there. Okay, so these are our different types of production functions that we will work with in this course, essentially. Okay, so now that we have all of that figured out, let's talk about how these firms will make decisions, and particularly how they make the most optimal decisions. And there's actually two main schools of thought, I guess not schools of thought, but ways that they can go about this, which are cost minimization and profit maximization. So cost minimization, they have some kind of cost function, which is a function of their quantity they produce, right? They produce some amount of output, and that costs something. We can actually do better than that because we already defined what the function of our output is, right? It's some function of labor and capital, and we said that those are the only inputs that matter. Those are the only things that we're spending money on in our firm. So under that assumption, we can actually just define our cost function, in this case, as the wage rate times how much labor we hire, plus the rental rate times how much capital we hire. Okay, so that is going to be our cost function, and we want to minimize that cost. We can't choose W and R, those are set, but we can choose L and K. And so we're going to minimize our costs, and it's subject to the constraint that we have, because otherwise our cost would be 0. So what are we aiming for? We're aiming for some amount of output. So at some given amount of output, we want to minimize our costs to reach that output. So that output is going to be some Q bar, and we'll use a Cobb-Douglas example. So L to the 1/3, K to the 1/3 is our production function. So we have some constant output, and we want to minimize our costs. And so we know how to do this, that we can just take a Lagrangian. This is constrained optimization right here. So we can write our Lagrangian. This is our objective function, WL plus RK. And we're going to add lambda times Q bar minus L to the 1/3, K to the 1/3. Okay, and so we take our first order conditions. This is the derivative with respect to L. We get W minus lambda 1/3 L to the negative 2/3 K to the 1/3. Okay, the derivative with respect to K is going to be R minus lambda 1/3 K to the negative 2/3 L to the 1/3. And then the derivative with respect to lambda is just going to be Q bar minus L to the 1/3 K to the 1/3. And we're going to set those all equal to 0, and then we're going to solve for lambda and plug this back in, and then what we're going to get is W over R equals K over L. Okay, so what we have here is that the price ratio between our inputs, labor and capital, is going to be equal to our marginal rate of technical substitution. And that's a pretty familiar concept. Price ratio equals the marginal rate of technical substitution. That's always going to be true. All right, so at the optimal point, that's always going to be true. So we'll say that we'll solve for K here. K equals LW over R, and then plug that into our bottom equation. So we get Q bar equals L to the 1/3, and then LW over R to the 1/3. Okay, which cleans up to, that's what, L to the 2/3, W over R to the 1/3. Okay, so L to the 2/3 equals Q bar R over W to the 1/3. Okay, and thus L equals Q bar to the 3/2 R over W to the 1/2. Okay, that is our optimal amount of labor. And then our capital in this case, because of our production function, is going to be symmetric. So we're going to get Q bar to the 3/2 W over R to the 1/2. And these make sense, right? As we increase our quantity that we need to produce, then we're going to hire more labor and capital. As we increase the rental rate, then we'll hire more labor, less capital. And as the wage rate increases, then we'll hire less labor and we'll hire more capital, substituting that way. Okay, and you can see that this is HOD 0, right? Quantity is not measured in dollars, but if you multiply the wage rate and the rental rate by some constant, then it's actually not going to change your optimal amount of labor and capital that you're going to hire. Okay, you're going to get A over A. That's going to be A to the 0. So these are your optimal amounts of labor and capital, and that's cost minimization. And you can actually plug that back in to your cost function, and you get your cost now equals W, and where's your L right here? So that's Q bar to the 3 halves, R over, I just want to make sure I do this right, R over W to the 1/2, and then that's plus R times Q bar to the 3 halves, W over R to the 1/2. Okay, now pulling out what we can here, that's going to be Q bar to the 3 halves. We have that in both. We have here W to the 1/2 in both, and we also have R to the 1/2 in both, right? So that's actually going to be Q bar to the 3 halves root RW, and we're going to have 2 of those. So that is our cost function. And we did that by solving for what we call our conditional factor demands for labor and capital. We call it conditional because they're conditional on some quantity, some output that we need to produce. And we solve that by constrained optimization. But there's actually another mentality we can take towards making optimal decisions for labor and capital as a firm. That's the profit maximizing school of thought, I guess. So if we want to maximize our profit is just revenue minus costs, right? Well, our revenue, what is that? It's price times quantity, right? So we're going to take some price and multiply it by our quantity, and we have quantity in terms of our production function, so it's going to be L to the 1/3, K to the 1/3 times price. So price, L to the 1/3, K to the 1/3, and then minus our costs, where we already have our cost function right there, so it's going to be minus WL minus RK. And this is our profit function. What we want to do is we want to maximize our profit function. Okay. Choosing K and L to do that. And is it subject to a constraint? In this case, it is not subject to a constraint. Basically, the only constraint that we face in maximizing our profit here is the fact that our production function has decreasing returns to scale. So as I scale up L and K, as I scale up my company, my firm, then I'll face decreasing returns to scale. And so what optimal amounts of L and K am I going to choose? That's why I chose a production function like that instead of one with constant or increasing returns to scale, because if you choose one of those, then this stuff can get messed up. All right, so we'll just look at the decreasing returns to scale option. But let's maximize our profit. And so we're not subject to a constraint, so we're not going to do a Lagrangian. It's not constrained optimization. It's unconstrained optimization. So we will take first order conditions though. We'll take the derivative of our profit function with respect to L first. That's going to give us, let's see, P 1/3 L to the negative 2/3, K to the 1/3 minus W. And taking with respect to K, to get P 1/3 K to the negative 2/3 L to the 1/3 minus R, and those are both equal to 0. So if we go ahead and solve this, we can actually get rid of P in this instance, and that will just leave us with the conclusion that K over L equals W over R. So we reach that same conclusion, and we can solve for K, which is LW over R. If we plug back K into either one of these equations, it doesn't matter which, but we'll get P 1/3. Let's plug it into this bottom one. So we have K to the negative 2/3. We're plugging in LW over R to the negative 2/3, and then L to the 1/3. Am I doing that right? Yeah, I think so. Minus, K equals LW over R. Minus R equals 0, okay? So that's going to be, and we're going to solve for L here. So L to the 1/3 and L to the negative 2/3 is L to the negative 1/3, right? So we have P 1/3, LW over R to the negative 2/3, the whole thing. Okay, sorry guys, let's try this again. So we have 1/3 P R over W to the 2/3, I took the negative out, L to the negative 1/3, minus R equals 0, okay? So all of this is going to actually equal R, and we want to solve for L. So let's move L over. We have 1/3 P R over W to the 2/3 equals L to the 1/3 R, and then bringing R over here, we have 1/3 P 1/3 P 1 over R to the 1/3 W to the 2/3 equals L to the 1/3, okay? Therefore, if we solve for L, we'll have that L equals P over R W squared, okay? And I know what I did. I didn't cube P right there. Okay, so we have L equals P cubed over RW squared. All right, and so this makes sense. As we raise price, then we'll buy more labor, okay? And as we raise the wage rate, then that'll affect labor. And actually, so as the rental rate increases, this might be counterintuitive, but we actually will hire less labor because we are spending money on labor and capital, and it's not going to affect it as much as the wage rate, but it will still affect it because labor and capital are complements in production, and so we're going to hire less of both if the wage rate increases. Okay, so this is our optimal amount of labor, and then the optimal amount of capital is going to be symmetric, so it's going to be P cubed over R squared W. And you notice that these are both HOD 0, so you have, if you multiply prices and input prices by the price of receive and input prices by the same constant, then you're going to get A cubed over A cubed, and it's not going to change the optimal amount of labor and capital that you demand, right? So basically, these are your unconditional factor demands for your inputs, labor and capital. Those are conditional, these are unconditional. And you can plug this back in to your profit function, and you're going to get P. Okay, so there's a few things plugged in here. So we have P L to the 1/3. So we know what L to the 1/3 is actually. It's just that right there. So it's going to be, what was that? I just wrote that so weird. There's supposed to be a 3 on the bottom. That's why I'm getting tripped up. So P times L to the 1/3, which is P over 3. There we go. Let's put that 3 on the bottom. R to the 1/3, W to the 2/3. Okay. So we have P L to the 1/3, and then K to the 1/3, which is symmetric there. P over 3, W to the 1/3, R to the 2/3. Okay. P L to the 1/3, K to the 1/3 minus WL, and here's L right here. P cubed over R W squared minus RK. P cubed over R squared W. All right. So let's see if we can clean this up. That's our profit function right there. And that's going to equal P cubed over E cubed over 9RW minus, that is P cubed over RW minus P cubed over RW. Okay. And yeah. Shoot, I know what I did. That 3 was on the bottom and I forgot to cube it. So this should be 27 RW squared. That should be 27 R squared W. Okay, so sorry, but in this case, these are going to be 27 and 27. All right, sorry for those mistakes right there. So essentially, we can clean this up because if we multiply this by 3 over 3, then we get 3P cubed over 27 RW. And minus one of those, minus another one of those, you're just going to get P cubed over 27 RW. Okay, and that is your profit. So what we can actually do in this case, in both of these cases, is we can get a supply curve for our firm. We're making the assumption here of a perfect competition that allows us to do some things we wouldn't normally be able to do. But we can take our minimum cost, and we can say that our cost minimization, and we can say that our marginal cost is actually equal to the price, because price is marginal revenue here in this situation where we're a price taker. Okay, so we can take our marginal cost here. That's going to be the derivative of our cost with respect to quantity, and we're going to get 3/2 times 2 times q to the 1/2 root rw. Those are actually all rooted, I guess. So our marginal cost is 3 root qrw. Okay, and if that's equal to the price, we can get a supply curve from that. So if we solve for q, then we get p over 3 root rw is going to be root q. Therefore, q is going to be p squared over 9 rw. And that is our supply curve. Okay, we can actually get the same supply curve from the profit maximization problem. And all we have to do right there is we just have to take the derivative of our profit with respect to the price. That's it. Let's try that. So we get, what is that? 3p squared over 27rw. And that 3 and that 27 is going to give us p squared over 9rw. And that is our quantity supplied in both cases. So it is the same. All right, so that is cost minimization, that is profit maximization, conditional factor demands, unconditional factor demands, supply curves. And now, with all of that said, and all of that gone over, including the mistakes, that was a teaching moment. Okay, so basically, that's a little more complicated than just finding the optimal price for a price discriminating monopolist. That's going to be really easy in comparison. So essentially, when it comes to price discrimination, I'll just draw a typical monopoly graph from basic econ. So you have your marginal, you have your demand curve. From that, you get some marginal revenue curve right there, and you have some marginal cost for your monopoly as well. And the monopolist is always going to produce where the price equals where the marginal cost equals marginal revenue. Everyone is always going to produce where marginal cost equals marginal revenue. Okay, so you're going to produce right here, that's your quantity, but you're going to charge this price on the demand curve up here. Okay, so this right here is going to be consumer surplus. This above the marginal cost curve, this is all going to be producer surplus. And then this right here is deadweight loss, because these are transactions that could take place but are not because of the higher price. Okay, so that is what a monopoly graph looks like. When we're talking about price discrimination, there are 3 different degrees of price discrimination. Draw this monopoly graph again. So first degree price discrimination is perfect price discrimination. It means you charge everyone their maximum willingness to pay. So you're going to capture all of this surplus right here, and all of that is going to be producer surplus. Okay, so that's perfect price discrimination, or first degree price discrimination. Second degree price discrimination, I'm not going to talk a whole lot about, but basically second degree price discrimination is price discriminating, charging different prices based on quantity. So if consumers buy this quantity, then we'll charge that price. If they buy this quantity, you'll charge that price. So you have that much, that's a consumer surplus triangle, that's some more consumer surplus, but you're capturing more of that producer surplus for yourself as well. Let me redraw this, it's getting messy. And I'll go over third degree price discrimination, and we'll actually do a problem with this one. So third degree price discrimination is where you have, in your monopoly, you are charging different prices based on consumer characteristics. So you'll charge one group of consumers this price, and you'll charge another group of consumers this price, which is a similar concept, but you're doing it not based on quantity, but on the characteristics of the consumer. So let's take an example of this. Let's say that you are aware of 2 demand curves, 2 different types of consumers. So the first curve is 120 minus whatever the price is. And the second demand curve for the same product, but a different group of consumers, is going to be 45 minus 1/2 of the second price. Okay, and let's say in this situation, we're going to keep it simple and not have a varying marginal cost. We'll just say that your marginal cost is constant at 10, just for demonstration purposes. Okay, so in this case, we have our first quantity, our second quantity, our marginal cost, and we're going to produce where our marginal cost is equal to our marginal revenue. So let's go ahead and solve these separately, and we'll find out the prices and the quantities that will apply to both of these market segments. So I'll solve for P first. So P1 is going to be 120 minus Q1. Okay, this is the first instance. And so our revenue, if we want a marginal revenue, our revenue is going to equal price times quantity, right? So that's a 120Q minus Q1 squared. And our marginal revenue is going to equal 120 minus 2Q. And that is going to be equal to our marginal cost, which is 10. So if we solve that, we'll get 110 equals 2Q. Therefore, Q equals 55. And if quantity is 55, plug that back in. 120 minus 55 is going to be 100 minus 35 is 65. So the price, 65. So this is the quantity and price I will charge, and the quantity bought for the first market segment. And then I can just do that again for the second market segment. So we have second quantity equals, or solve for the price. So P2, 1/2 P2 is going to be 45 minus Q2. So multiplying that by 2, I have 90 minus 2Q2. All right, so our revenue for the second segment is going to be 90Q minus 2Q2 squared, saying that equal to 10, which is my marginal cost. Then, oh, sorry, I have to take my marginal revenue. So my marginal revenue is going to equal 90 minus 4Q2. And therefore, if that equals 10, then I have 80 equals 4Q2, and Q2 equals 20. Therefore, the price is going to equal 90 minus 40, which is 50. Okay, so I will charge the second group 50, and 20 will be bought. So that is how you find the optimal price and quantity charged in third-degree price discrimination for a monopolist. Okay. The only other concept that I would cover for producer theory that seems relevant is that we like to distinguish sometimes between the short run, the very short run, and the long run. In the very short run, we like to say that supply is fixed. Your quantity is fixed. You can't change your output. That's our definition of the very short run. Short run, we would say that there are some things you can change, but some things that are fixed. In our labor capital example, we would say labor you can change, capital you cannot. That takes a lot longer to change the amounts of capital you have in your company. So what you'll end up with in the long run, comparing the long run to the short run, here's a graph of quantity and price. So your long run curve will be pretty smooth. And if you remember this from basic econ, essentially on this side you have economies of scale, whereas as you are producing more, you have economies of scale, and you get more efficient. Okay, this is your average cost curve. But as you produce beyond a certain point, you have diseconomies of scale, right? You get less efficient. So you're going to want to produce right here, right? But in the short run, your curves are going to be less elastic. They're going to look more like that. So here's a short run curve for that point. Here's a short run curve for that point. Here's a short run curve for this point, right? These are all short run curves because in these cases, we'll say that your capital is fixed. You can't change it. These are the short run. And if your capital is fixed, then the only way you can produce more is to hire more labor. That can get really expensive really fast. So that's why these short run cost curves are more inelastic. But this is more representative of the long run, which is very elastic. Or in some cases, say it's perfectly elastic. Okay, but that's under a lot of assumptions. That's generally what the company looks like. And the difference between short run, very short run, and the long run. Before we end, we've gone through all of consumer theory, we've gone through producer theory, and there's one more thing that would be good to talk about. That would be partial equilibrium. And it's going to be different from general equilibrium. General equilibrium is where we consider the effects of different markets and different industries. Partial equilibrium, we are just going to look within our industry, within our market, and we're going to ignore effects outside of it and interactions with the outside world. This is how partial equilibrium might go. If we have some problem, let's say that we're going to make some assumptions. We're going to say that every firm in a particular industry has a cost curve that looks like Q squared plus 9. Okay, we can see that everything in terms of Q, that's their variable costs, and everything not in terms of Q, those are their fixed costs, right? Okay, fixed costs, variable costs, and every firm we're going to assume has this cost curve. And we're also going to say that we know what the demand curve for this market is. We're going to say the demand curves looks like 90 minus 5p. Okay, that is the demand curve for the entire market. Well, if we know these two things, there's actually a lot that we can do with this, and this is partial equilibrium theory. So first of all, we know our marginal cost, right? That's pretty easy to get. Our marginal cost is going to be 2Q. We can figure out our average cost. We just divide by Q to get that. So our average cost is going to be Q plus 9 over Q. That's our average cost. That's a 9. Try to distinguish between my 9s and my Qs here. We know our marginal cost. We know our average cost. But from this, we can actually get a short-run supply curve because our supply curve is just our marginal cost curve above our average variable cost curve. In this case, actually, is always going to be above our average variable cost curve. But we're going to set our marginal cost equal to price because we are price taking in this scenario. We're assuming perfect competition, right? And so in that case, we can get a supply curve. So our marginal cost, 2Q is going to equal the price. Therefore, our short-run supply curve is going to be P over 2. There we go. We got a supply curve just from our marginal cost. And so we can also look at what our output is going to be in the long run. In perfect competition in the long run, we know that our marginal cost is going to equal our average total cost. So if that's true, then 2Q in our firm is going to be equal to Q plus 9 over Q. Therefore, Q is going to equal 9 over Q. Q squared is going to equal 9. Therefore, in the long run, we're going to produce 3. That's going to be our optimal long run quantity. Okay. Perfect. Okay, so we have our long run quantity where our marginal cost equals our average total cost. We can do that. If we have our long run quantity, we can also find out the long run price as well, right? Because we know that our marginal cost equals the price. So 2Q is equal to 2Q equals the price. Well, Q is 3, so then the price must be 6 in the long run. Okay, that is the long run price. It's going to be 6. Well, if we know the long run price, we can also get the long run quantity because we have this demand curve right here. Okay, so if price is 6, then the long run quantity is going to be 90 minus 5 times 6, that's 30. So that's 60. 60 is the quantity demanded in the long run. And if we know that 60 is the quantity demanded in the long run, and that every firm with this cost structure, which is all of them, is going to be producing 3 in the long run, we actually know how many firms there are as well, right? So that means that, well, there's 60 being produced total. Every firm is producing 3. So the number of firms is 60 over 3, which is 20. There are 20 firms. Therefore, we can actually take the supply curve for each of these 20 firms, and we can use it to get the market supply curve. Because there's 20 firms, all of them have the supply curve of P over 2. Therefore, the market supply curve is going to be 10P. There you go. That's your market supply curve right there. Okay? So that is partial equilibrium. Okay? Let's graph this, why not? Okay, so here's a little graph. Here's quantity, here's price. And we know that in the long run, we're producing where the price is 6, and the quantity is 60. Okay? So for our quantity demanded, 90 minus 5p, that puts, let's say we have 90 out here, and 18 or so we have somewhere up here. So we have this demand curve or something that looks like it. And then our supply curve is 10p, right? So it's going to start at 0, and then it's going to cross at 60. Okay, so here's 90, here's 18. It's going to cross at 60, so somewhere around there. Okay, and that's our supply curve. So that's 60. That's the price of 6 right there. Okay, more or less. More or less, that's what it looks like. That is our equilibrium right there, 16.6. And now we can observe what happens in different situations with this equilibrium. Let's say there's a tax put on us of $2. Somewhere around here, there is a $2 tax. And that means what? That essentially means that the price paid by consumers minus the price received by producers, supply, equals 2. Okay, that is the amount of the tax. So that area is going to be 2. So we can actually say that the same thing as saying that the price received by consumers is PS plus 2. Okay, well, since we know that, then the quantity is the same. The prices are going to be different, but the quantity is the same. So let's set those quantities equal to each other. So we have quantity demanded, 90 minus 5, and this is going to be the price demanded, so that's PS plus 2, and that is going to be equal to 10 PS. Okay, and now here we can solve for PS. So we have 90 minus 5 PS minus 10 equals 10 PS. So getting rid of that 5 PS, that turns into 15 PS, and that's 80 right there. 80 equals 15 PS. So that means that PS equals 80 over 15, which I believe is about 533. That seem right? 15 times 5 is 75. Yeah, exactly. So PS is 533, which means that PD is going to be 733. Okay, so these are the prices in this case where there is a tax of $2 on this good. You can see that it affected the consumers more than the producers in this case. Look, the price was 6, so producers are getting 66 cents less, but consumers are paying 133 more. Is there a way we can kind of see or predict that happening? Well, yeah, there's actually a little cool formula. You can say that the change in the price paid by consumers relative to some tax is equal to this SP is the derivative of supply with respect to P. And it's going to be over that derivative minus the derivative of, minus the derivative of demand with respect to P. And this is going to tell you how much of the burden of this tax is borne by consumers. So you can plug that in. And what's the derivative of supply with respect to P? Well, we got 10P, so that's just going to be 10. It's going to be over that 10 minus, and then we got negative 5 over here. So that's going to be altogether 15. Okay, or in other words, consumers are going to bear 2/3 of the tax burden in the case where there's a tax. That's just because of elasticity. If I had drawn this a little bit better, you probably would have seen that demand is more elastic than, or supply is more elastic than demand. So consumers will bear more of the tax because they're more inelastic. Okay, so they bear 2/3, which they did, and then the other third is borne by the suppliers in the case of this tax. Okay, so that is what happens with a tax. A subsidy is the opposite of a tax, and a tax, and that tax right there, this much would be deadweight loss, right? With the subsidy, we're over here, and this much is deadweight loss. So it's just kind of the opposite of a tax. All right, so that's taxes and subsidies. Other things we can examine: if there's a price ceiling, let's say the price is lower, the government sets that, so then there's going to be some kind of shortage, and more is demanded than is supplied, or a price floor is a similar concept. So we can examine price ceilings, price floors, how those influence these different markets. And one other thing that we're going to examine before we close out here is going to be what happens in cases of international trade. So I think my dashed lines are straight enough. So this is, let's say this is an economy that trades, and there's some world price. The equilibrium would be 6, but because they trade, right now the price is 4. Okay, so since the price is 4, okay, what happens if, for example, there's some, and in this situation, I'll just clarify that this right here, this right here is imports, right? They're producing this much, but they're consuming this much. So they're importing goods because of the lower world price, okay? So what happens if there's a tariff of $1, okay? And it raises this. That bottom one is the world price. But then there's a new price, and there's a tariff of $1. Okay, what happens in that scenario? What happens is that, whereas before we had this much was producer surplus, right? This triangle right here. And this whole big triangle going all the way up here to the world price, okay, that's consumer surplus. So what happens in the case of a tariff is consumer surplus goes down, okay, goes down to here. They're importing less. You can see that they're importing that many goods, difference between those two. Importing less, consumer surplus goes down, producer surplus goes up. And then the amount that they end up importing after the tariff, okay, times the amount of the tariff, that's a G right there. That is government revenue. These two triangles on the sides, these are deadweight loss. Okay, so that's how you could calculate all of these triangles. You could put this into a problem, but that's how graphically you would describe the case of international trade and a tariff. And with that, I think, unless I missed something, that we covered everything that I think is relevant, at least in producer theory, consumer theory, and in partial equilibrium theory and related concepts. So hopefully that's helpful, and thanks for watching.